Thank you. Welcome, everyone. Today, we are here to talk about something foundational, something fundamental. But this foundational thing will not be LLM related. Today, we are here to talk about the work that B2 Impact does to manage something that has been with us for a very long time, financial risk. But before that, I believe that we need to make some small alignments around the terminology and concepts that surround our industry. So first of all, why is important financial risk for B2 Impact? B2 Impact is a pan-European debt specialist. And we will see more in detail what that means. But basically, our company focuses in investing in loans. When we invest in these loans, we purchase them, and we become the owner of them. And after that, we manage them. We operate in 15+ countries across the whole Europe. And across 2.5 years ago, we embarked ourselves in a journey to become the industry leader in data analytics. For that, we built 2 teams of data engineers and data scientists, now joined into a single team. The purpose of this team was mainly to automate all of the processes that we need to have to manage these loans, and also to make the best investment decisions with regards to the purchases of this loan. Concretely, B2 Impact focuses on what we call non-performing loans, or NPLs. But to understand what an NPL is crucial to see how the debt industry works. So we are going to see this with an example. Imagine that you go to the bank and you ask for a loan. If you receive the loan, you will become a customer of the bank. If you end up with us, you will be called also a debtor. Debtor and customers of the bank are interchangeable terms. If everything goes as planned, nothing will happen. However, sometimes the borrowers of these loans, they default. So that means that either they have not made any of the scheduled payments, or either they are late in some of them. When this situation happens, the banks, they decide to sell these loans, and they call them non-performing loans to the market. So investors and entities like us decide to purchase them. And we engage in a blind auction process where we bid for these loans. These loans, they don't come in a single fashion. They come in chunks, and that's why we usually call portfolios. The portfolios, they can be heterogeneous, containing different kinds of loans, car loans, credit cards, etc. Or they can be homogeneous and be of the same type of loan. The reason because we engage into this blind auction process is because our operational structure differs from the bank. We have the data, the competences, and the processes to manage these loans better. And that's why usually we value them more than the banks. But apart from that, apart from the difference in operational structure, data, and competences, there is a fundamental difference between the banking sector and our industry. Since the introduction of the IFRS 9 regulation, banks, they are obliged to calculate the expected credit loss, which is a risk measure. The expected credit loss is basically the probability of default of a given loan multiplied by an impact factor. In this case, the loss given that default, the exposure at default, which are the cash flow through the whole lifetime of the asset, and a discount factor. In our industry, we also need to calculate expected credit losses. But the variable for optimization is different, and is what we call expected credit recovery. You can think as the expected credit recovery as our ability to reactivate a loan. In reality, these 2 variables, they are 2 sides of the same coin. ECL doesn't exist without ECR. One could think that the ideal situation is that the ECL is 0. So that means that the banks and lending institutions, they make perfect decisions. In that case, the credit flow would be heavily restricted because they will have to be much, much safe. Also, you can think that a bad situation is when the expected credit loss is high, and the expected credit recovery is low. Because that means that the system as a whole will have net losses. There will be some debts that they will not be possible to recover. But actually, that's not the worst case scenario. The worst case scenario is where the expected credit losses are high and the expected credit recovery is overestimated. Because if that happens, the banks, they will not adjust their lending policies or their systems to give less loans, because they will have always someone that will buy that loan. And at the end of the day, if that happens and the portfolio that we purchase is mispriced, the system risk will increase exponentially, and at the end, it will collapse. So that's why it's so important that we evaluate our portfolios properly. Before I hand over to Abel, I would like to point one small thing. Because our loans, they have defaulted when they purchase them, the cash flow of these loans is what we call zero-inflated. So that means that most of the customers of the bank, they will not pay when we have acquired them. They did not pay when they were with the bank. And during the first month of acquisition, the cash flow will be zero until we manage to reactivate that cash flow. I will not talk today about the methods that we have to deal with zero-inflated data. But if someone is interested, you can reach us at the end of the conference, because we have an online talk talking about this fact. And the final thing that I would like to clarify is that when we say unveiling precision, a novel framework to calculate accurate probability estimates, for us, accurate probability estimates, they go beyond a number. They are about quantifying the uncertainty in the probability predictions. Concretely, in the case of the probability of default or probability of reactivation, in this binary decision problem, there are different frameworks to do that. Mostly conformal prediction with prediction sets, conformal prediction with confidence intervals, and calibration. We do not have the space today to discuss the whole three, but my colleague Abel today will talk about calibration. So having said that, the stage is yours.
Imagine you are in a room with a big investor. To be specific, a debt purchaser. He wants to purchase a portfolio of defaulted debts in order to recover them. The idea is to recover more money than the price he pays. However, he has a problem. His valuation tool is not able to estimate a fair price of the portfolio. And guess what? He wants you to do it with machine learning. With an imposing voice, he tells you to stand up, because he's going to tell you something very important. He stares at you as you have never been stared at before. In this situation, he takes out a briefcase. And he says, "This is the money I want to invest." And he opens. €20 million. He proceeds. All the uncertainty your model can have will produce losses of this order of magnitude. One question is clear. You want not an excellent estimate, but the best possible one. The reason, tiny improvements can be translated to thousands of euros. Let's pause the story here and let's see the technical details. In some markets, current valuation tools are not able to estimate a fair price for the portfolio. And the reason is that they have difficulties to estimate the cash flow coming from high payments. This leads to a wrong valuation affecting profitability. Why are high payments so challenging? Let's see it in a real data set of a debt collection industry. Here, high payments are those payments higher than or equal to 10,000. Two main ideas to extract here. First, high payments are an extremely rare event. And second, the feature space is poor, low predictive power. Therefore, if we try to train a classifier, we obtain this result. We trained different models and we sorted them to illustrate how challenging problem and data are. As you can see, for example, one of the top models of the table has a precision of 0.06%. That means that when the model predicts high payment, it is correct only 6% of the time, which is pretty bad. And the remaining metrics are equally bad, suggesting that with the feature space available, we can only detect small changes in the probability. As you can see in the formula that Edgar introduced, predicting well these slightly different high payment probabilities is crucial in order to estimate in the best possible way the expected high payment amount. At this point, a spoiler. With the proposal of this talk, we can correct portfolio prices by hundreds of thousands of euros. So you want to know how to do it? Let's see the plan. We concluded that we need to select the model with the best probabilities. For doing that, we need to assess calibration. However, widely employed tools are not perfect and can lead to wrong conclusions. Recently, this produced a lot of research. To solve that, we applied to the finance sector. It's not working, okay? We applied to the finance sector a solution based on a new metric to address those issues. So this is the structure for the remaining part of the presentation. Let's start with calibration. Reliability diagrams. Imagine a binary problem, PEA versus non-PEA. For that problem, you constructed a probability estimator to give scores to each debtor. The score space is commonly discretized into n bins, so you will have multiple samples per bin. The idea is to compare the average probability score with the actual fraction of positives in each bin. Normally, you would think that the closer the points to the diagonal, the better the calibration. However, this is not exactly like that. Because remember that because we are dealing with random variables, the average score is not the only possible outcome, even assuming well-calibrated probabilities. In fact, you can have a high likelihood to have a model that is well-calibrated, predicting points that are not close to the diagonal. For this reason, these charts are normally drawn with confidence intervals. Of course, these diagrams are useful. They can help to detect miscalibration regions, and they are a visual and powerful tool for stakeholders, and we employ them. However, they are not perfect, and the choice of binning can influence the assessment of calibration. In fact, inappropriate binning may obscure underlying patterns and can lead to wrong and biased conclusions. Furthermore, if you want an automatic assessment, a graph is not normally the best option. Normally, the thing you want is a metric that summarizes the information of the graph to do the automatic selection. So how to create that metric? The popular answer is with the expected calibration error. Conceptually, the ECE is based on the difference between the average probability score and the actual fraction of positives in each bin. Different types of norms, L1, L2, can be employed, as well as different ways of weighting each bin. For instance, in function of the bin length or the number of samples in the bin. However, these metrics inherit the drawbacks of binning. Inappropriate binning may obscure underlying patterns and can lead to biased and wrong conclusions. Here you have recent research that supports these claims. The summary. Widely employed tools can fail. And this raises a question. The question is, would it be amazing to have a metric that yields trustworthy results without needing large samples because of the binning and without needing to set any parameter like the bin length, mathematically proven, simple, robust, and easy to compute? Guess what? That metric exists. They are called the ECCER and the ECCEMAD. Here you have the expression. They are based on the empirical cumulative differences. They are proved to be simple, more robust, easy to compute, more reliable, needing lower amounts of data, and non-parametric. No bins, no kernels, no other things. Here you have additional references to see why they have these properties. And in the second one, you can find the written form of this presentation for those of you who want additional details. So knowing that, we created a pipeline to apply this to the finance sector, where we create a set of models with different calibrators. Being uncalibrated, also an option. Then we assess the best ensemble in function of the proposal, the ECCER. This way, we have an automated and reliable solution to select the best probability estimator. So some results. This slide is just to illustrate why usual metrics can lead to wrong conclusions. Here you have the evolution of the expected calibration error for 4 different models. And as you can see, depending on the binning, the ranking can change. In fact, what it seemed to be the best at the beginning ended up being the worst at the end. And this is the type of issues that we want to avoid because they can lead to wrong conclusions. Here you have a more reliable table based on the proposal, the ECCER. So what happens when we use the proposed metric in finance applications to guarantee this more appropriate model selection? Well, in the high payments problems we introduced, we are able to get better estimates in the order of hundreds of thousands of euros because of the better probabilities due to the better model selection. In the slide, you have some numbers just to get an idea of the order of magnitude of how these small corrections can impact in the final outcome. In other expected recovery problems, like when we try to predict the cash flow coming from legal procedures, in some cases, we are able to get metrics 10% better thanks to the best probabilities. For example, one metric interesting for us is the desired ESMAPE. In another use case, we employed these scores to design a better call strategy, to decide which group of debtors call first and with which priority. Using the better calibrated estimates, we achieved an increase of 2% in payer rate and 10% in collections. And this leads to the conclusions. So a machine learning pipeline is proposed, considering a new metric in the assessment of calibration to improve propensity to pay models in the debt recovery industry. We showed that the proposal with the ECCER is more convenient, robust, and reliable for an automated selection. This is crucial in the industry if you want a solution with minimal degradation, without manual intervention, and without large human costs for constant evaluation.
To almost conclude, I just would like to mention that besides this contribution to the community with the paper and the slide deck, we have decided to make a small pull request to scikit-learn. So in there, you will have the ECER and the ECMID implemented to run cross-validation functions or just to run the normal metric. And if you think that this is interesting for your business or for your industry, I welcome you to either improve or pull request or either to upvote it if you would like to have it merged.
To end up, I would like to finish the story we post, the one about the purchaser and the briefcase. After implementing the solution, the debt purchaser came back and said, this contains the remaining money we want to invest. And he opened. Empty. Do you know what this means? Maybe the data inside has the answer. Dear modeling team, I hope this letter finds you well. You might be wondering why the briefcase is empty, and the reason is simple. After implementing the solution and observing the results, now we are able to always find the best investments. And therefore, we no longer need it to keep our money in a briefcase. And we decided to invest it all with the help of your tools. Now the money is in the right asset. Thank you. Sign it, the debt purchaser. One of the reasons why I wanted to tell this story is the following. Some people think that AI is lack of emotions. They think it is very analytical, logical, and mathematical. Even some, they think that the latest advancements are due to become called mathematical intelligence. And maybe that is true. However, if this is skyrocketing in our society, it's because of the power of transforming emotions. Children nostalgia at hearing their dead grandparent again, thanks to AI. Or the love an artist feels when an AI or when exploring a new art made by a machine. Or the excitement an investor sees when an AI can improve his returns. AI is plenty of emotions, and this is what is changing the world. I hope this will not be the last time, but the first we meet. For the moment, let's close this chapter and see you in the next. Thank you.
You can start. Yeah. Abel and Edgar, thank you so very much. It was truly a privilege to have you on stage. Thank you so much for a wonderful and interesting and entertaining presentation. We have some time, we have a few minutes before we're going on lunch for a question, so do think about your best question, and we can start off already here in the middle, with this person can start off.
Hi, thank you for your presentation. It was very interesting. When you create a probabilistic model, how would you value AUC versus calibration? Imagine you have a model with higher AUC but lower calibration, or a model with a little bit lower AUC and higher calibration.
Yes, good question. In the pipeline, first we create like a set of models with strictly scoring proper rules that these evaluate the discriminative power of the classifier, and then when we add the second layer, that is the calibrator, is when we evaluate basically the calibrations assessment. As we did this first step to guarantee a good discriminative power, then in the second step we can just focus in the calibration part.
Just to complement to Abel's question, remember that we are predicting risk, and risk is probability multiplied by an impact factor. So what is relevant for us is to have the best probability, not to have the best UC. Because at the end of the day, we are using this as a valuation tool. And the final outcome is not only the probability, but it's how much money are we going to get returned from the portfolio.
Great. Remember, the best question earns the briefcase of money, we can say. Yeah, I have a quick question as well. So, what are the implications of the EU AI Act when it comes to machine learning applications within the financial sector? Is there any changes coming up for you guys and any extra considerations that you will have to think about going forward?
So definitely this is something that our compliance department is looking. And in the previous talk in the other room, we talked about differential privacy and federated learning. So that might be something to look into. But so far, what I can say is that even that this UI Act is coming and GDPR, this varies quite a lot from country to country. I mean, you need to remember that we are a holding operating in 15 plus countries, so not every country have the same regulations. There are some countries where, for instance, we cannot upload data to the cloud. So in that sense, it depends. Definitely it will have effect, but unfortunately we need to consider this case by case. We cannot come with a global framework because of the implications of the fact that we operate in so many countries.
Yeah, that's a compliance office issue. Any other question in the room? Yes, one right here.
Now you presented this matrix, but can you also consider using this matrix to improve the calibration of the model, or they're just measuring, or you can also use them as some form of regularization, loss function during the training, or maybe post-trainings, temperature scaling, or stuff like that?
You can try to do an hyperparameter tuning job with these metrics. For example, in the case when you guaranteed a base discriminative power, but they should be implemented like in the framework that you want to use normally.
So at the moment you're just using them for best model picking, not to change the model itself.
Yes. Also to guarantee also a baseline discriminative power. And when we use this in the second layer, because for us, because this is just a part of a more complex ensemble, we need to guarantee, or we should be very, very sure that this reflects real probabilities in order to get a better estimates.
Right. Okay. Thank you.
Great. Thank you all so much for the wonderful questions. And thank you so much for the wonderful presentation. Give them a hand.
Thank you.